Good afternoon and good morning to attendees from other parts of the globe attending this webinar. My name is Charlie Bender and I'm an AIST staff engineer, and we are gathering now with attendees from several different continents to learn about Decarbonization 102, the hydrogen iron-making, managing expectations of H2 transformation and its many colors. This is a webinar co-hosted and presented by the AIST Decarbonization Subcommittee and the AIST Young Professionals Steering Committee. Welcome. For an AIST webinar, the attendee audio has been disabled. Questions to the presenter should always be submitted through the question and answer feature in the Zoom software. Our host and moderator will determine which questions are then presented to the presenter. This session is being recorded and will be available for demand and replay on AIST website under Webinar Archive. Photos or recording of the presentations is prohibited, and if you should run into technical difficulties, please by email use training@aist.org for technical assistance. AIST always presents with two policies in mind: the antitrust policy of the United States government and an anti-harassment law. We do not discuss with others or our own competitors' pricing, and we don't make statements about prices about other competitors. We don't talk about individual companies or what our plans in a market might be, and we don't disclose any other competitively sensitive information. Please do not propose or agree to any action intended to disadvantage or injure a third party, and do not stay at a meeting or activity where any such anti-competitive talk occurs. At AIST, we expect to have a comfortable meeting and exchange of networking capabilities with everyone. Please do not harass, and at AIST leadership, you could be expelled from the event or from AIST membership. I'd like to take a moment to introduce our moderators. Our first moderator is Britt McKinnon. She is an employee of Hatch, and she comes to us with an excellent educational background and work already in the pyrometallurgical and hydrometallurgical sections of Hatch, including projects that have covered greenfield feasibility studies, practice on an integrated steelworks expansion, due diligence reviews, new steelmaking plant site selections, and most recently a hydrogen iron-making study. In the hydrometallurgical sector for Hatch, she has also worked on a battery recycling pilot plant, advisory practice, and catastrophic risk assurance program. Most exciting for us, Britt is active with the AIST Young Professional Steering Committee and is a decarbonization liaison representing the AIST Electric Steelmaking Technology Committee. For the chapter, she has been the previous young professional for the AIST Northern chapter, and currently, while residing in Australia, she's active with the AIST Australian member chapter. In 2021, Britt received the AIST Presidential Citation Award for her contribution as a young professional and a rising leader in this association. I'd like to now introduce Joe Maury. Joe has degrees in chemical engineering and petroleum refining from the Colorado School of Mines, an MBA from the Indiana Wesleyan University, and he's a master black belt certified through the Villanova University. Chronologically, starting in 1995, Joe has worked for U.S. Steel Corporation in Gary, Indiana, Granite City, Illinois, has been in Pittsburgh, Pennsylvania, Kosice, Slovakia, and now in Gary, Indiana again, in positions including iron-making, steel-making, sintering, blast furnace technical team lead, and coke and iron-making. In Pittsburgh, through the Munn Hill Research and Technical Center, he's covered Lean Six Sigma, Green and Black Belt consulting through a consulting team. And moving to Slovakia, he's covered as general manager the primary operations for sintering, coke making, iron making, and steel making at that site. Now in Gary, he is currently working as a senior consultant in process innovation, where he is the lead for Greenhouse Gas Tactical Task Force. At AIST, throughout his career, he is currently the vice chair of the Ironmaking Technology Committee and in the decarbonization lead role during participation as subcommittee of the Energy and Utilities Technical Committee. I'd like to turn over the presentation now to Britt, who will present our first presenter.
Thank you. It is my pleasure to introduce you to our first presenter, Mike Grant. Mike completed his bachelor and master's of applied science degrees in metallurgical engineering at the University of British Columbia in Canada. Mike started his career in 1988 working in ironmaking for Inland Steel Co. as a blast furnace process engineer. Nearly 10 years later, at the end of 1997, he joined Air Liquide to develop and commission burner and oxygen injection systems for electric arc furnaces, EAFs. In 2001, when Air Liquide purchased American Combustion, ACI, he began working for ACI, designing and commissioning oxygen injection systems for EAFs. Since joining Air Liquide, he has designed, successfully commissioned, and optimized more than 30 EAFs worldwide. In 2007, he was transferred to Air Liquide's research labs just outside of Paris to work on EAF and blast furnace topics, most notably the European Commission ULCOS project, ultra low CO2 steelmaking. When he was on the European Learn team developing the top gas recycling blast furnace, he remains in Europe to this day, based in Frankfurt, Germany. In his current position, he uses his technical and operational expertise in the steel industry to develop Air Liquide's and long-term strategies towards decarbonization of the steel industry. He's invited every year to speak at the AIST Modern Electric Steelmaking Technology Seminar, and the author of 59 and counting technical publications and 8 patents. Without further ado, I'd like to pass it over to Mike.
Thank you very much, Britt, for that kind introduction. I'm very happy to be here today to speak to the AIST Decarbonization Subcommittee and the young professionals. And I look forward to addressing your questions after both of us speakers have talked. Just a quick inquiry about my presentation is in view? Good. Okay, so the title today is Orderly Transformation from Blast Furnace BOF to Hydrogen-based DRI with either electric arc furnace or submerged arc furnace and BOF steelmaking. So what can we expect? Well, I'm going to do something a little bit different. I'm not going to talk about green, blue, or gray hydrogen, just hydrogen. I'm going to assume that the availability of green electricity, sufficient green electricity is assumed to be available. We're not going to talk about the cost of decarbonization because we all know this is a very significant endeavor that we need to take. Instead, I'm going to assume everything's everything is green, available, affordable, and I'll first talk about the blast furnace, then move on to direct reduced iron, and then finally the use of that direct reduced iron in either electric melting, arc melting, or electric arc smelting, as they call it. And this will enable me to focus on other problems besides the ones that I'm avoiding higher up in the list. So let's start with the blast furnace. The blast furnace, this is a classic blast furnace picture. You might find something like this in a textbook. It is a very basic. It shows quantities in terms of per ton of iron. And it has the three most important reactions that take place, starting from the charging of the iron ore, Fe2O3, all the way down to the reduction of FeO to iron. And this, I'm not going to say more about this. You've all seen this before, those of you who are familiar with the blast furnace. But I'm going to move on to something a little bit more fundamental. Now, if we look at the operation of a blast furnace, we can characterize the blast furnace using a blast furnace map. I like to call it a map. And what is it? It is a shape. And we look at fuel injection versus oxygen injection. And we can see that we have this shape here, which actually defines the limitations of a particular blast furnace. They're not the same in every blast furnace, but this is an example, and you can see the reference point is shown here. And this reference point is about 180 kilograms of pulverized coal injection per ton of hot metal, and with an oxygen injection rate somewhere in the neighborhood of 65 or 70 cubic meters per ton of hot metal. And you can see these limitations are defined by the outline of this shape. And we can move around in this shape and we can bang up against these limitations. But if we increase our oxygen and increase our pulverized coal injection, theoretically, we can reach this point up here, which is our maximum productivity. The furnace operation itself is bound, this example is bound by a maximum raceway adiabatic flame temperature of 2164 degrees Celsius, which actually follows the same line as this minimum top gas temperature, which is actually the true limitation. It just happens to be the same with that raft temperature. We have a minimum top gas temperature limitation, and we have a maximum top gas temperature limitation. And these are pretty classic limits that are defined by most operators. And you can see also this maximum top gas temperature coincides with the minimum flame temperature. So as long as we operate within this range here, we can operate the blast furnace fairly smoothly. If we can achieve our maximum coal injection, which is defined here as 250 kilograms, this will allow us, with combining it with oxygen, to save up to 7%, or to increase the productivity up to 7%. Now let's look at the CO2 emissions. Well, if we're just looking at the direct emissions of the blast furnace, we see that they start to increase as we increase our coal injection. And why is that? Because the coke replacement ratio is less than 1. So we have to inject more than 1 kilogram of coal to replace 1 kilogram of coke. And this increases the overall direct CO2 emissions of the blast furnace. And you can see, as I said, they increase with PCI injectant. And of course, we all know that coke rate goes down with increasing pulverized coal injection. And that's why we do use coal injection. We want to minimize the coke rate as much as possible. But how much CO2 is emitted from the coke making process? So we can get pretty good, you'll see later on, pretty good calculations of CO2 emissions reduction in the blast furnace, in just looking at the blast furnace itself. But we have to consider also that when we are increasing our PCI, we're also decreasing our coke rate. So the graph turns into this type of graph when we include coke making on the direct CO2 emissions y-axis. And so if we consider a coke plant located at the integrated steel plant, so the CO2 emissions of that coke plant are included in the overall plant emissions. And given that coke making, assuming that the coke oven gas is used elsewhere and the users take the credit for the CO2 emissions from using that coke oven gas, we can say the coke making process uses somewhere between 400 and 500 kilograms of CO2 per ton of coke. And assuming that we can reduce our coke production when we minimize our coke rate, we can say that PCI, we can calculate that PCI reduces the CO2 emissions by about 5%. So not so much, but nevertheless, it looks a lot better than the previous graph where we showed the CO2 emissions of the blast furnace increasing as we increase coal injection. So overall, we get a net reduction in CO2 emissions. So, but still, 5% is not very much. And so everybody in the recent years has been talking about hydrogen in the blast furnace. And the reality is we've been injecting hydrogen in the blast furnace for many decades. And this was steam injection, of course, was first, I think, documented in the Soviet Union in the 1920s. And by injecting steam into the tuyeres of the blast furnace, you get a reaction with the hot coke inside the raceway, and this makes hydrogen. And of course, this is very endothermic and causes you to, it requires a coke increase to cover the endothermic energy that is being absorbed. But it was found, the hydrogen that was created was found to actually smooth out the operation. So a furnace that's moving or descending erratically, little bit of hydrogen actually helps smooth it out. And the reason for this is because the hydrogen is a small molecule. It tends to diffuse more rapidly into the iron ore particles, therefore improving the reduction. And this can decrease the amount of FeO in the primary slag. FeO will leak out of an iron ore particle, touch the hot coke, get reduced, and freeze. And this has a detrimental effect on the permeability and can cause problems with burden descent. So the hydrogen helps relieve that. Later on in the 50s and 60s, oil and gas were being injected into the blast furnace, and these have a lot of hydrogen in them themselves. And this helped also improve the operation of the blast furnace. Hydrogen has other benefits such as aerodynamic benefits. It can improve the permeability of the furnace. Another limitation is the pressure drop from the tuyeres to the top of the furnace. This is dependent on a permeability represented by the constant K and the density of the gases inside the furnace. We call them Bosch gases. As we put a lot of hydrogen into those Bosch gases, this density goes down, which actually lowers the delta P between the tuyeres and the top of the furnace. And so this has, in some cases, allowed for a little bit higher productivity. And so not only do we see the CO2 emissions going down with hydrogen injection, but we also can experience some smoother operation. So what does hydrogen do in the blast furnace? Well, you saw in that first diagram I showed you, they had the reactions, the reduction reactions with CO. Well, hydrogen replaces the CO in the reduction, directly replaces it. And you can see the three main reduction steps being undertaken with hydrogen. And you'll see that these are the energies required for this hydrogen reduction. Now you notice here that there's a net endothermic effect when we do all of our indirect reduction with hydrogen. If we compare that to CO indirect reduction, CO indirect reduction is actually exothermic, so it contributes energy to the process and therefore helps reduce the total energy requirement of the furnace. Looking at the lower part of the furnace, we start to react water with coke. This is highly endothermic, and the total direct reduction is a very endothermic process. So The net effect of hydrogen reduction in a blast furnace is equivalent to roughly 90 kilograms of extra carbon that needs to be charged to cover the endothermic nature of these reactions. So this is one of the issues that needs to be dealt with when we use hydrogen in any iron reduction process. If we look at the map of 100% hydrogen injection versus oxygen consumption, we see our limitations get squeezed very quickly. So we're limited by low top temperature and low flame temperature. And as we inject more and more hydrogen, we have to inject a lot more oxygen until we reach this point where we're at our minimum flame and top temperature. And this is our limitation, which is only about 27 kilograms of hydrogen for this particular furnace. So these are the limitations of the furnace. And in fact, we don't even reach our reference. In this case, we don't even reach our reference productivity. This effect, of course, is furnace dependent. So this little green map here was it was the same as the one I just showed you. And a larger one is for calculations I did for another furnace. And this particular furnace can actually accept up to 47 kilograms of hydrogen, which is quite unusual, but it's very furnace independent. And in this case, this particular furnace would be able to get more benefit out of the hydrogen injection. It's dependent on many different things. The reference productivity, of course, is very important. If the furnace was already at close to its maximum, the permeability has an effect. And of course, how much auxiliary fuel rate was being injected prior to the hydrogen being introduced. Like the PCI graph, when we inject more hydrogen, we reduce our blast furnace and coke making direct CO2 emissions. Using the same assumptions that the coke plant is located at an integrated steel plant. The same emissions for making coke. And assuming that we can reduce the coke production, we can get a small decrease in CO2 emissions from injecting hydrogen. And this is about 10%. And it's not very much. The blast furnace emits about 1.5 tons of CO2 per ton of iron that it makes. So if we are able to reduce 10%, that's only about 150 kilograms. And this, of course, is not really going to be acceptable for contributing to energy transition. So in Europe, they're moving away from the blast furnace. But first, let me explain other issues. So for example, we can start with 0 kilograms of hydrogen. We can inject, in this case, up to 19 kilograms of hydrogen and reduce our CO2 emissions by about 10%. But then as we increase further, we have to keep adding coke. And you see, we're injecting more and more hydrogen. We're replacing PCI, but it's not, we have to add coke to cover for various things, even the endothermic nature of the reaction, but also the fact that we're bumping up against the limitations that I showed you in the blast furnace map. If we look at these blast furnace maps, you can see why we're bumping up against these limitations, and this is causing us to require to increase the coke rate in order to maintain our top gas temperature or our flame temperature while we inject more and more hydrogen. Looking at this graph from a coke rate standpoint, you could see, well, the reason we get success in the initial hydrogen injection is because we're able to maintain our coke rate. We're replacing PCI with hydrogen until we get to this point here. And this is very low coke rate. These are theoretical numbers, but it explains the effect. And then at this point, the coke rate needs to be increased again. And when we finally replace all of the PCI, we're back up to about 400 kilograms of coke. And this is why normal operators would stay in this region here, the coke rate inflection point. However, there is a productivity benefit, and you see if we co-inject PCI with hydrogen, we can actually increase the productivity of the blast furnace beyond the limitations of the original operation with PCI. So if this is the maximum theoretical production rate with PCI, and we mix a little bit of hydrogen in there, we can actually get another 6% increase in productivity on a theoretical basis. The same effect is also true with natural gas, although you need a higher amount of natural gas in order to get this maximum productivity benefit. But nevertheless, there are some benefits to injecting, co-injecting hydrogen and or natural gas with PCI. This maximum productivity point is also the point of lowest CO2 emissions. So if we can achieve that and get around other limitations, practical limitations that the blast furnace might have, we could actually kill two birds with one stone, reduce our CO2 emissions while increasing the productivity of the blast furnace. So, but here in Europe, most of the major steel companies now have announced that they're going to switch to direct reduced iron, because of this, limitation that hydrogen has with the blast furnace. 10% is not enough, and so the steel companies are being forced to plan for direct reduced iron making with either submerged arc furnace or electric arc furnace steel making. And here's an example of some calculations that were done for melting steel to make steel in the electric arc furnace. The reference, of course, is 100% scrap. And you can see this is not a model furnace. It's a rather unimpressive performance, but 480 kilowatt hours per ton is not so uncommon. And 22% normal cubic meters of oxygen. If we replace 75% of that scrap with DRI and a high carbon DRI, which is desirable, we can maintain our chemical energy by adding a little bit more oxygen, but our power consumption goes up, and it goes up considerably by about 70 kilowatt hours per ton. And this reduces the productivity of the furnace by about 11%. And so this is one of the drawbacks of DRI, but you'll be reducing your CO2 emissions. If we go further and replace the natural gas reductant with 100% hydrogen, now we're making a DRI that has no carbon in it anymore. And so it's going to be more difficult to melt it in the electric arc furnace. We'll have to back off on our oxygen in order to maintain our yield. And we see this chemical energy is no longer available, so we have to melt with more electrical energy, and we lose another 7% or 6% productivity. So this is one of the issues we're going to have to deal with when we start using electric arc furnaces to melt DRI. Now, there's two processes or two routes being anticipated here in Europe. One of them is the high carbon DRI being charged into a submerged arc furnace, which is producing a high carbon hot metal. And this high carbon hot metal will be further refined in the BOF, just like they were doing in the first place. To get the carbon in the DRI, of course, you need natural gas. This natural gas deposits carbon in DRI, and you need at least 3.5% weight percent carbon in the hot metal in order to be able to use it in the BOF. And why do they want to do this? Well, one of the issues with producing low nitrogen steels is we rely on the CO bubbling to purge the nitrogen from the steel. And this is one of the important reasons why the BOF it's hopeful that the BOF can be kept. The other thing, of course, There's a shortage of DRI grade pellets, which are very high iron content pellets. And this method would be allowed to enable you to use blast furnace iron ore pellets, which have a higher slag volume. And because the submerged arc furnace is a reducing environment, we don't have the problem with FeO in the slag. And the higher the slag volume, the more FeO you lose, so your yield goes down. Nevertheless, in this case, you don't have the benefit of chemical energy like you do in the classical electric arc furnace. And so we can anticipate a higher energy consumption in the submerged arc furnace. Nevertheless, you can benefit from this CO purging of the nitrogen that will be dissolved in the steel. Some companies have announced that they're going classical DRI route. So there's natural gas, which will produce a DRI with carbon. The carbon content is not as important. And this will be melted in a classical electric arc furnace, which has an oxidizing environment. This requires DR grade pellets. The electrical energy requirement will be lower. It'll be more difficult to purge the nitrogen from the steel. And of course, we're going to see lower steel yields than in a BOF. So there's a trade-off depending on which route is chosen. Now, I did a little thermodynamic simulation of carbon deposition in the pellets during DRI making. And you can see that we can put carbon in the DRI even if we start adding hydrogen in the mixture with the natural gas. And theoretically, at least, and it's been published also, that you can get up to 5% carbon in the DRI, which is good. That's chemical energy we can use in the steelmaking process. And so this is quite achievable, thermodynamically at least, and evidently practically. And so we can make a hot metal if we want to. However, I'll go back, I went back too fast. However, DRI, it's impractical to reduce all of the iron units to metallic iron. And typical merchant DRI is about 94% metallization, which means 94% of the iron content in the DRI is metallized. This means about 7.6 or 8% FeO is in the DRI. And so when we produce a high carbon DRI and we melt that high carbon DRI, this FeO is going to be the first, it's going to attack this the carbon first and use up quite a bit of the carbon. And so if we manage to produce a 5% carbon DRI pellet and we melt that pellet, we're only going to produce somewhere around 3.5 to 3.7% carbon in the hot metal, which doesn't give us a lot of room for use in the BOF. So evidently there's going to be a need, whether it's a high carbon DRI or a low carbon DRI, we're going to need to get carbon into the process. We're going to lose about 1.3% of the carbon that was deposited in the DRI just through a reduction of the residual FeO that's there. What does this mean if we're using it in a BOF? Well, let's compare with classic hot metal with 4.5% carbon, 0.6% silicon. And let's say we can melt 25% scrap and 75% hot metal. Pretty good ratio. Sometimes we can go up to 70 or up down to 70% hot metal. Depends on the silicon content in the hot metal. Now, when we melt DRI in a submerged arc furnace, we're going to see very little silicon, experts tell me. And so this silicon is chemical energy from the oxidation reduction. And just from this loss of silicon, it's going to limit how much scrap we can use. And in fact, we'll have to go from 25% scrap down to 13% scrap. And this problem gets worse as the carbon content in the hot metal decreases. So 4.5% carbon in the DRI gives us only 3.2% carbon in the hot metal. Without silicon, this brings our scrap ratio down to 10%. And finally, at 3% carbon in the DRI, we will not have enough energy, chemical energy remaining to melt that, to melt any scrap. And this scrap, increasing the scrap ratio is one of the key strategies for reducing CO2 emissions. So we got a problem here, and of course it all boils down to how we get this carbon in the hot metal. So in the future, of course, we want to change this to hydrogen. This is going to produce a DRI with no carbon or little or no carbon. We'll need carbon injection in both the submerged arc furnace and the electric arc furnace. And so the reducing environment, of course, will require carbon injection. We'll be able to we need to put that directly in the metal, which means it's got to go through the slag and dissolve quickly in the hot metal. So we want the carbon in the hot metal. This means we need a fluid slag. If we have a blast furnace type slag, this shouldn't be a problem. Blast furnace type slags are designed to be rather fluid, so you can get it out of the tap hole. And so we need to be able to inject the carbon through the slag and into the hot metal. Efficient carbon injection is going to be, in my opinion, one of the key technologies. And it sounds simple, but it's going to be one of the key technologies that makes this concept work well. If we look at the electric furnace process using the classical electric arc furnace, a traditional carbon injection is used to control the FeO content in the slag, because we're in an oxidizing environment. We're oxidizing quite a bit of our iron units. It's making FeO, which is going into the slag. We got to recuperate some of that FeO. We do that with carbon injection. And this also, if we do this correctly, if we treat the slag correctly, we get slag foaming too, which is a thermal benefit. It reduces yield loss and prevents over-oxidation. So we don't damage our refractories with excessive FeO in the slag. However, conventional carbon injection systems in today's EAFs are around 50% efficient, which means you lose about half of it into the fourth hole, into the exhaust system, where it travels down into the dropout box and smolders and makes CO2 with no benefit whatsoever. So just a few things to think about. I'm just giving you my final remarks. For the blast furnace, hydrogen injection has limited benefits, unfortunately. The blast furnace itself is such an efficient process. It won't benefit much from hydrogen injection when we're looking at CO2 reduction. About 10% is what we can expect if we're counting the emissions from coke making. And this is the reason why in Europe, almost all the major steel companies are looking to retire their blast furnaces when it's economical to do so. Looking at steelmaking, the injection of carbon into the metal bath is going to be critical. We need to do it much more efficiently than we do today. We need to be able to produce a hot metal suitable for the BOF. And this can only be done with carbon injection. And the traditional EAF needs also to be able to use low carbon DRI. And so carbon needs to be efficiently added. We have to compensate for little or no silicon dissolved in the hot metal if we're using a submerged arc furnace. And again, carbon efficiency is going to be the key to saving or making this much better. So I think this is the challenge for the future. Doesn't sound like a real, it sounds like a small thing, but it's actually going to be, I think, one of the key developments that enables all of these steelmaking routes to be successful in a low carbon world. And with that, I really appreciate you listening to me, and thank you very much. And I'm looking forward to our question and answering after the session's over. Thank you.
All right. Great, Mike. Thanks for all that great information that you gave to us. Just to let everybody know that's on the webinar, we do have your questions and keep them coming in the Q&A box. We'll get to those at the end of the session so we are able to get through both webinars. It's my honor to introduce Dr. of Engineering, Dominic P.J. Bars. He's an associate professor at the Department of Chemical Engineering, Queen's University in Kingston, Canada. After a vocational training as a construction mechanic, he studied mechanical engineering at the Aachen University of Applied Science in Germany and graduated with a Bachelor of Engineering in 1996. He then held several positions in industry and public sector, so in companies such as Mercedes as a lab engineer in the Benz fuel cells lab, and a senior research engineer working on the lab on a chip technologies in Karlsruhe in Germany. During these full-time employments, he pursued further part-time studies and graduated with a diploma engineer with distinction process engineering from the Technical University in Dresden, a Doctor of Engineering Science with a distinction of mechanical engineering from the University of Karlsruhe, now the Institute of Technology, KIT. From 2007 to 2008, he was a visiting fellow at the Cornell University in the US, working with Professor Paul Steen on interface and transport phenomena. In 2010, he joined Queen's University as a faculty and took up the post of an associate director of the Queen's RMC Fuel Cell Research Center. He is the recipient of several prestigious awards, including the Helmholtz Association Microsystems Scholarship, the ASME Outstanding Leadership Award, in Ontario Early Researcher Award, and the DAAD Research Scholarship. During 2016 through 2017, he was awarded the Alexander von Humboldt Research Fellowship that he spent with Professor Stefan Hart at the Center of the Smart Interfaces in the Technical University of Darmstadt, Germany. He's authored more than 50 peer-reviewed publications and has given more than 40 invited presentations at conferences, webinars, seminars, workshops. His current research interests comprise electrochemical interface and materials engineering with an emphasis on graphene and supercapacitors, batteries, and water electrolysis. I'd like to introduce you to Dr. Bars.
Hey, thank you very much. I tried to share my screen. Then we can get going. So, does that
That's
work?
very good.
Excellent. Thank you very much. And thank you very much for the kind introduction. I know I'm rather at the end of my career almost. Therefore, my CV is a little bit longer. So the title of my talk today is gray, blue, green, purple, the many colors of hydrogen. And maybe let's say in contrast to the previous talk, it will be more general. And we will take a different look of hydrogen and the transition to hydrogen economy, and maybe what the problems are. So my talk the content of my talk is, I start with some facts, easy facts of hydrogen, and then I go into the production, storage, applications. For what actually do we need hydrogen? I mean, we need it for many more applications than steel and iron making. And then I come to some conclusions. So facts, very simple facts. Hydrogen comes from hydrogène, which is French for a water producer, because water is made out of hydrogen. Chemical symbol is H. We all know that, hydrogenium. It's the first element in the periodic table because it's also the simplest one and the lightest. So it has the lowest atomic weight. It's around 1 gram per mole, which is the molar mass. Consists of a charged nucleus, which we call usually a proton, and a negatively charged electron. And we have it in forms of isotopes, and then it contains small neutrons. It's the most important element in the universe, and it's estimated that 75% of the universe consists of hydrogen in one form or another. But hydrogen on Earth, we rarely find in the elemental form. We always find it in as a compound of another molecule. So usually on Earth, we have it in the largest proportion comes in the form of water. And almost all organic compounds have also hydrogen. And fossil fuels, so hydrocarbons, are primarily made of hydrogen. And the higher the hydrogen content of or the hydrogen to C ratio of hydrocarbons, the lower its greenhouse gas emissions during combustion. That's what we are interested in.
Apologies, Dr. Bars, for interrupting. Would you
Yes.
please ensure you're showing the presentations view? We see your next
Oh.
slide in notes as well. Thank you very much.
No one told me. So how about now?
Wonderful, thank you.
I'm sorry for that. No, hang on. I have to change it once more because now I'm sorry. I have to change it once more because now my notes are gone. So what do you see now?
We see your notes still.
Okay, hang on. How about now?
Perfect.
Excellent. Good. Made it. Thanks. And sorry for
welcome.
that.
All good. Thank you.
Okay, so if we take a look at hydrogen as a fuel and compare it to other fuels, we see that it's a really good fuel because it contains more energy per unit of mass than natural gas or gasoline. And it makes it really attractive as a transport fuel. But on the flip side, hydrogen is the lightest element, and therefore we have to store that unit mass. We need a very high unit volume. So this makes it very difficult as well as a fuel for our energy demands compared to other fuels. So I would like to go on now and talk a little bit about the production of hydrogen. There are different methods to produce hydrogen. Technically, we can distinguish between fossil fuels and renewable sources. Fossil fuels are all carbon-based compounds which have hydrogen. And here we can do reforming of hydrogen and pyrolysis of hydrogen. And for the reforming, we have different methods, and I will briefly talk about these a little bit later. So we have steam reforming, partial oxidation, or the thermal reforming. And because we use hydrocarbons, we will always make carbon dioxide in them as well. So we have renewable sources. On one hand, we have biomass because we can grow biomass, it's considered renewable, and we can convert the biomass into hydrogen somehow. But I don't want to talk about that. And then we have water. We can split the water and gain and make hydrogen. And because when we have hydrogen and oxygen, we can make water again. It's also considered as renewable. So some general facts are that 70 megatons of hydrogen are produced by year, and this is only the dedicated hydrogen. So there's much more hydrogen produced, but then usually as a side product, for example, in the oil refinery processes. Here from that 70 megatons, 76% comes from natural gas and 23% come from coal. And this consumes kind of 205 billion cubic meters of natural gas, which is around 6% of the global use. It also consumes 107 megatons of coal, which is around 2% of the global coal use. It's responsible for 830 megaton of carbon dioxide emissions per year, which is the annual carbon dioxide emissions of Indonesia and UK together. So electrolysis is only responsible for about 2% of the global hydrogen production right now. If we would like to change that, and that all hydrogen is produced by electrolysis, we would need 3,600 terawatts per year, which is more than the European Union annual electricity generation. The water requirements are fairly high as well. We will need more than 600 million cubic meters of water, which is more than 1% or around 1% of the water consumption of the global energy sector. It's 2 times of the water consumption that we require to make hydrogen from natural gas. Just to put that a little bit into perspective, what happens when we make everything with electrolysis. So depending on how we make hydrogen, it became a kind of a fashion to assign a color to it. And the color indicates kind of the greenhouse gas footprint. And in the following slides, I will show you a little bit what it means to have green hydrogen or pink hydrogen or blue hydrogen. But before that, I would like to talk about water electrolysis, because for green and pink and blue hydrogen, no, green and pink hydrogen, this is the technology that we use. So water electrolysis is that we use electricity to create hydrogen oxygen, whereas the oxygen is rather a side product because it has not a very high value. To do that, if I have one molecule of 1 mole of water, I need electricity around 240 kilojoules for a mole. And I also need heat around 50 kilojoules for a mole of water. And then I would get a mole of hydrogen and half a mole of oxygen. There are different types of electrolyzers, which can be categorized according to electrolytes. So we have the alkaline water electrolyzer, we have the proton exchange water electrolyzer, and then we have a new technology which is coming into the market, which is called solid oxide electrolyzer. Because of the time, I just talked briefly about the proton exchange membrane water electrolyzer, because this is probably the most advanced technology nowadays. Maybe not the most installed technology, but the most advanced technology. So what we have here is 2 electrodes and a membrane, and the membrane is acidic and it keeps the electrolyte, and the electrolyte is acidic as well. So it means it has a lot of protons, H+. And then we have 2 electrodes, and at the one electrode, it's called cathode, we have a reduction. So the protons takes up electrons and will make the hydrogen. And at the other electrode, at the same time, we have water, which is splitted or oxidized into protons that half mole oxygen that we gain and in electrons. So this is how the PEM water electrolysis works on a very generic level or general level. The advantage of this technology is that it has a very low temperature range, just 20 to 90 degrees Celsius. We can achieve very high current densities, more than 2 amps per square centimeters. That's very high. It also has a compact system design and very good dynamics. It delivers a high purity of gases, and the energy efficiency is also good. So energy efficiency means how much energy do we lose for making the hydrogen, or is related to the losses. So the higher the energy efficiency, the higher is the or the less energy we spend on making the hydrogen. The disadvantage of the technology is that the cathode, the one electrode, is made from platinum and palladium, which is already expensive, but the anode, it beats that. It's made from iridium oxide and ruthenium oxide. And as far as I know, the annual world production of iridium for iridium oxide is around 5,000-6,000 tons per year, which is nothing. And this is one of the major problems that this technology has. Also, the durability is limited because of the very harsh conditions. So we have very low pH values. It's very acidic. Anyway, so electrolysis is the main technology that is used for different hydrogen production processes where we put different colors or assign different colors to. So we have the electrolyzer that we feed with water and oxygen. So the electrolyzer needs electricity, and if the electricity comes from renewable energy like photovoltaic or wind, then we call that green hydrogen. And this has minimal greenhouse gas footprint. Let's say, and that's very simple thinking. It's only if the entire process chain is made also with renewable energy and not maybe with an energy mix which has a high carbon dioxide emission. Anyway, of course, we can also use nuclear energy. For example, I live in Ontario, and we have a very high fraction of nuclear energy in our electricity mix. And then we call that pink hydrogen, and it has also a minimal greenhouse gas footprint. And then we have, usually in other countries, for example, Germany, you have a mixture of different energy sources. So you have renewables, you have carbon-based technologies like coal power plants, and you have nuclear and hydro. And when you have that, you call that yellow hydrogen, the hydrogen that you make, and the greenhouse gas footprint is considered medium. So this is a different electrolysis production methods that we can have. Of course, we can make hydrogen with a conventional chemical process. And one of these processes is steam methane reforming. So we have natural gas that we clean usually, and then we reform it. That means we add water to the methane and heat it up. And maybe we have a catalyst, probably we have a catalyst. And what we produce is a syngas consisting of carbon monoxide and hydrogen. And this syngas can further be converted into more hydrogen and carbon dioxide in the so-called water gas shift reaction. And then maybe we can capture the carbon or maybe not. So this is an endothermic process. It needs something like 206 kilojoule per mole. But I don't want to go into more details than that. Then we have methane pyrolysis. This is the catalytic decomposition of methane. So methane is split into carbon and hydrogen. And it's a very good process in technical because we don't have or hardly have carbon dioxide emissions because the carbon comes as a solid product. However, it operates also at higher temperatures, and it's a mildly endothermic process. Just to give some perspective, if we put in 4 tons of methane and 5 megawatt hours of heat, we get 1 ton of hydrogen and 1 ton of 3 tons of carbon as a solid. Then we have gasification. So we can have things like we can have carbon from coal, or we can have biomass, and we add oxygen and hydrogen here. And again, we make a syngas similar to the methane steam reforming, which can be further converted in water gas shift reaction to make more hydrogen and carbon dioxide. So these are the main chemical processes that we use in reactor. And then again, how we process it before, or depending on the feed and how we process the gas that we get from the reactor, then we can assign different colors to the hydrogen. So the most conventional thing is blue hydrogen. Here as a feed, we have methane or coal. We feed that in the reactor, and we do it with reforming, steam reforming usually. What we make is hydrogen and a carbon dioxide. And now we have the opportunity to capture that carbon dioxide. There are different technologies, physical, chemical. And because we filter out the carbon dioxide from the emissions, we have a low greenhouse gas footprint. Then we have gray hydrogen. That's just having methane. We do the same reforming, the same reforming process. We get again hydrogen and carbon dioxide, but we don't remove the carbon dioxide. That's kind of the standard industry process. And then this is gray hydrogen with a medium greenhouse gas footprint. Then we have turquoise hydrogen. Here we have methane and pyrolysis. Feeding in the reactor, we get the solid carbon and the hydrogen, and it has a low greenhouse gas footprint because, again, we get the carbon as a solid and not in form of carbon dioxide, and the carbon has no greenhouse gas effect. And finally, we have brown and black hydrogen. Usually you distinguish between them, but it only is a difference in feed. So if you use brown coal, it's brown hydrogen. If it's black coal, it's black hydrogen. You do gasification, again, you get carbon dioxide and hydrogen, and you have the highest greenhouse gas footprint from all the processes that I have shown. And the brown is worse than the black. So let's switch to storage. One of the problems, or the problems of hydrogen, is that it has such a low density, which means we need a high volume to store it, which is difficult. So we distinguish between physical-based and material-based storage mechanisms. So physical-based is that we compress the gas or we liquefy. We do a liquefaction of the hydrogen. And we have, of course, a method where we do both, so cold and compressed. And material-based, there's many different alternatives that we can use. We can absorb it in MOFs, so metal organic frameworks. We can use it we can do hydrogenation in liquid organic material. We can dissolve it essentially in a metal. So we do a hydrogenation of metal, for example, lanthanum nickel 5, which is a battery element. So the nickel metal hydride battery works like this. So it's stored in the interstitials of the metal frame. Or we can do chemical hydrogenations, for example, ammonia. And I will talk about that a little bit. So physical-based storage, essentially we either cool it down or we compress it. If we cool it down, that's the area 1 here indicated, the blue one. So we cool it down to, I don't know, minus 250 degrees Celsius. And then we get kind of relatively high density. And this liquid hydrogen is commonly used for hydrogen storage in transportation. The advantage of liquid hydrogen is that we can use a pump rather than a compressor. And pumps are much more reliable and refueling can be done much quicker. If we go to high pressure, then we usually do that at ambient temperature, so 293 Kelvin. Then we pressurize the hydrogen up to 600 bars. We see that the density is less, the volumetric compared to the liquid hydrogen. That means the energy content is less. But this is usually used for fuel cell vehicles. And the tanks are, of course, it's a challenge to have a tank which stands pressures up to 700 bar. So these are usually high-tech carbon composites. And then you can, of course, you can use both. You can use cold and pressure, and then you get a higher energy storage density than the other two processes. However, we have to say here that this is tricky also. So if I do the compression of hydrogen to, I don't know, 350 to 700 bar, it takes around 10% of the energy which is stored in the hydrogen. So we lose that essentially. And if I turn it into a liquid by cooling it down, it needs almost 3%. 30% of the stored energy. So it's a big challenge storing hydrogen so that we can use it. Just a nice picture. The NASA was the world's largest user of liquid hydrogen when they were operating the space shuttles. So of course, it's expired, but here we see a liquid hydrogen gas tank of NASA, which were used to fuel the rockets of the space shuttle program. Another concept to store hydrogen is to put it into caverns and store it underground. And this compares to other large-scale energy storage systems. For example, pumped hydro facilities. I'm not sure whether you're familiar with that, but in Germany, it's fairly common. If the energy demand is low during the night, but of course you don't want to turn off your power plants, you use the energy, the electricity, and pump water up a height. So maybe in a lake which is above a certain level. And then during the day when you need energy back, you let the water flow down and it goes through turbines. And here, for example, we have the power plant in Geesthacht in Germany, which has a volume of 3 million cubic meters and a height of 83 meters, height difference. So the energy stored here is 500 megawatts. There's also the idea to store compressed air underground. There's a plant in Hunddorf in Germany as well. So you have a cavern which is 300,000 cubic meters. Then you pressurize the air, you pump the air into it, pressurize it up to 50, 70 bars, and then you decompress it if you need it and run through turbines. And the energy storage is around 580 megawatts here. You can do the same with hydrogen. So you pump hydrogen into the cavern, and then you up to, let's say, 60 bars. And this energy content is 40,000 megawatt hours in thermal energy. And if you assume you use a fuel cell and the efficiency is something like 40%, it's still 16,000 megawatt hours. So it's a much higher energy density in the same facility compared to compressed gas. Then we have also the opportunity to do hydrogenation. So we synthesize a chemical using hydrogen. And another element, for example, ammonia. So ammonia production is a very well-established industry. There's a lot of nitrogen on Earth, so we don't have to worry about that. And it's fairly easy to release the hydrogen from the ammonia when we need it back. It's also the methods for the transportation of ammonia are well established. And they can be used for other things as well. So if we have liquefied ammonia, it has 120 kilograms of hydrogen per cubic meter. And this happens at ambient pressure and minus 33 degrees Celsius. And if you compare that to liquefied hydrogen, so this we need minus 230 degrees Celsius and 4 bar, and then it has only 70 kilograms of hydrogen per cubic meter. And if you compare it to compressed hydrogen at 700 bars and ambient temperature of 20 degrees Celsius, it only has 42 kilograms of hydrogen. So this is might be a valuable approach to store and distribute hydrogen. And there are many more chemicals that you can use or make to store the hydrogen than ammonia. I just took it because it's one of the most common things. So let's talk a little bit more about application. So most of the hydrogen that are used nowadays is for ammonia production, so fertilizer is essentially, or for petroleum refining, hydrocracking and upgrading, methanol production, and other chemical processes. Then if we go to the transport sectors, so fuel cells, buses, trucks, cars, it's almost negligible, or trains nowadays as well. There are fuel cell trains as well. This is an interesting figure that I found in the internet. So it predicts the hydrogen, or it tells us the hydrogen adaptation in some industries and how it will develop. So nowadays, there's only 2 industries which utilize hydrogen or dedicated hydrogen on a larger scale. This is refining and chemicals, so chemical industry. And in future that will stay like this, but certain other industries will catch up. For example, iron and steel. So it's predicted coal and coke replacement up to 2050, that this is kind of an established thing. And of course, you can prove me wrong, but I'm not an expert on that. I just took that figure from the internet, from the source. Right? Transport sector also in 2050, we will have penetration of considerable penetration of hydrogen in it. As a power fuel, so energy storage and grid support, these people predicted it will never be used. And this has some certain reasons. I will talk about that on the next slide. And for blending of gas, so we substitute natural gas with hydrogen, this will also catch up to 2050. It will be a large scale industrial process. So why wouldn't we use hydrogen as energy carrier? So here we have a diagram where we plot the discharge time of a technology over its power rating. So for example, we see that batteries can only be discharged up to days, but the power rating is wide. So essentially the area that we see here in the color of batteries, that tells us something about how good the technology is as an energy carrier or energy storage system. This is one thing, because hydrogen can be discharged for a long time, and depending on the technology, whether we use a fuel cell or maybe we use it as a thermal fuel, we also get a very high power rating. But the color here indicates the efficiency of the processes. And we see that the efficiency of everything which is fuel cell, hydrogen, is not that high here. That's the reason that the efficiency of making hydrogen with electrolysis is already limited, and the efficiency of a fuel cell is also limited. And when we combine these 2 processes, electrolysis and fuel cells, we get relatively low efficiency. So most of the energy that we put into the process is gone and it's not stored. And this might be the reason that the people predict that hydrogen will never be used as an energy storage fuel. But I'm sure there are different opinions about that. What is used nowadays is the application in oil reforming. So there are different things we do with hydrogen. We remove sulfur from crude oil, and we upgrade the heavier fractions of the crude oil. We do hydrogenation, and this is also applied to a smaller extent to the oil sands, that's biofuels. That's oil sands, that's a Canadian thing. There is the expectation that there will be a 7% higher hydrogen demand by 2030. This is boosted by tighter pollutant regulation, so we need lighter oil. But it's also expected that the oil demand the growth is moderated, and therefore the long-term demand highly depend on the future of oil. But here we have to say that 65% of the hydrogen that we need in refining is met by hydrogen, which is supplied as a byproduct already from crackers or catalytic reformers. So it's not replaced. It's not very likely that we replace it by low carbon hydrogen made by electrolysis or something like Application for chemical production is a very wide range of production. I already talked about ammonia, so the Haber-Bosch process, which we need for fertilizers, and methanol is also very important. And just to give some predictions for future trends, in 2000, we kind of needed 30 megatons of hydrogen per year for the ammonia production, which mainly went into fertilizer. And there will be also only a mild increase to 2050. Still, we will use most for making fertilizers. So for methanol, the increase is much higher. So we had not even 5 megatons demand of hydrogen per year in 2000, but in 2050, it's expected that it's almost 25. And this mainly goes into fuels and additives and processes where we need methanol as a precursor, for example, for olefins or aromatics. Finally, so application for iron and steel production. Of course, this was all covered much better in the previous talk, and I don't try to pretend that I have technical knowledge about that. I just give some numbers here. So in 50s, we produced something like 190 million tons of crude steel, and in 2019, exactly 10 times more. So 1,869 million tons. This is kind of 24% of all industrial carbon dioxide emission is attributed to steelmaking. So that's a huge number. Or if you make it to all industrial, to all human carbon dioxide emissions, that's almost 10%. And if you, just another interesting number, if you would like to convert Europe's steel industry, which might be not that big anymore, but I'm not an expert here, to hydrogen-based production of direct reduced iron, and if you would like to cover the electricity by renewables, you would need 50,000 wind turbines. Not to mention the infrastructure that you need for 50,000 wind turbines. And that's the dilemma of the iron and steel industry. It is expected that the output of crude steel and pig iron goes up to plus 41% up to 2050. But in the Paris Agreement, we said we would like to keep the 2 degrees Celsius target, and so that limits that means that the emission intensity of the iron steel industry must be lower to minus 2/3 of its present values. We all know there are different processes for making iron and steel, and I don't want to talk about that because it was just made. So maybe I just switch to the emissions. So if we keep our traditional blast furnace and basic oxygen furnace, we emit kind of 2 tons of carbon dioxide per metric ton of steel produced. If we go to the direct reduction, where we have the syngas and the electric arc furnace, we cut it down to 25% of that value around. But if we further use dedicated hydrogen made from somewhere else and not from the syngas and the electric arc furnace, we cut it down to 10%, essentially. There's also an electrolytic reduction process, but I'm not sure how relevant it is. But maybe you can tell. So just to summarize my talk, hydrogen has added benefits of meeting the industrial demand and also to help with the decarbonizing of the processes. The cost of green hydrogen produced by electrolysis nowadays is still significantly greater than blue hydrogen produced by steam methane reforming with carbon capturing. And that's, of course, is a major hurdle to implement electrolyzer technology. In terms of hydrogen as fuel in transportation energy storage from renewables, I would say the future is unwritten. Everything is possible, that we drive around with fuel cell cars in 50 years. instead of battery cars, or that we have a mixture, maybe the trucks are mainly powered by hydrogen and fuel cells. But again, the crystal balls usually don't work that well. That's at least my experience. So I would like to thank you very much for your attention, and I'm happy to talk about, and I'm happy to take some questions. So.
All right, hi, if we could get Mike also on here, great. Okay, so we have a ton of questions and we have like 8 minutes left. So I just wanted to mention to the audience not to be nervous, because all the questions are going to be stored for you guys, and you'll be able to get those questions responded to by the authors of these presentations. So really good there. Also, if you look in the AIST.org, you can download the presentation most likely next week. That the recording will be available, not the presentation, but the recording. If you want to get the presentation, you need to contact the presenters directly for those slides. Okay, we'll go to Britt with the first question.
Okay, our first question from Mike is, what stage is the submerged arc furnace technology at? And are they injecting carbon now?
The submerged, for the steel industry, the submerged arc furnace technology is very, very new. And there's only one operation that I know about that uses it. It's at Steel Dynamics, and they have their own direct reduced iron process called Iron Dynamics, which takes a composite, a mixture of iron materials, not necessarily iron ore, but it could be waste materials. They mix it with a carbon, typically a coal, I would imagine. I don't know for sure. And the intimate contact of these of the iron oxide with the carbon does the reduction. So when they reduce, when they melt it, there's not that problem with the FeO that we that I described that you would get with pellets that were reduced in a DRI reactor. So that's so it's to make a long answer short. That's the only example I can give, and there's no, as far as I know, there's no carbon injection.
Okay, great. Thanks, Mike. I got a question for Dr. Bars. Seems like with this hydrogen, there's a lot of energy, extra energy that's going to be required vis-a-vis the current processes that we have now. Can you kind of relatively, with all the processes that you described, which are the high ones that have the higher energy demands and which are on the lower side? Because this might ultimately talk about the ultimate cost of these types of processes.
For what? For storage or for?
No, for the generation of hydrogen.
Oh, generation of hydrogen. Usually, probably the cheapest process is steam methane reforming. It's a thermal process. You don't need a fancy reactors for that. It's also not a high pressure process. And that's the thing, right? So if you compare it to an electrochemical processes are usually always more expensive because we use electricity as a power source, and that's much more expensive than heat. It's already a higher form of electricity. Maybe in future it may come down where we use a lot of renewables. I mean, and that's one of the basic ideas. When we have a lot of renewable energy right now, we cannot store it. We can't, sometimes we have too much wind. We can't just feed it in the grid. The power grid is not a storage. So sometimes we just have to turn off the mills. So the idea is maybe to use that excess energy, which is lost otherwise, and we use it to run an electrolyzer. And then we can say, well, it's better, the costs are better than lost energy. But generally, electrochemistry is more expensive than chemical industry or electrochemical industry.
Excellent, thank you. And our next question is for Mike, and it would be, how are the lime additions impacted by the use of low silica hydrogen-based DRI in the steelmaking process?
Okay, if we're talking about the submerged arc furnace, we can, and one of the reasons for choosing the submerged arc furnace is the ability to use blast furnace grade pellets in the DRI process, which has a higher slag volume. And ideally, I would imagine that you would choose a flux pellet, maybe with a lime to silica ratio similar to what you would have in a blast furnace, say roughly a 1.1. And the intimate contact of the silica that comes from the ore and the lime that was added to the pellet would cause a fluxing during the melting, and you would get your slag, your low FeO slag, because it's a reducing environment. The lime additions would come into play in the BOF process itself, where you would have to balance any silica that probably mostly would come from the scrap with lime additions in the BOF process itself. So you would certainly use lime would be consumption would be reduced, and that would be solely in the BOF.
Okay, great. So, I got a question from Ephraim Masawe. Physical base storage, this is for Dr. Bars. With the properties that is required for the storage, is it best to produce this hydrogen on site?
Yes and no. It has clearly an advantage if you don't have to distribute everything, right? But on the other hand, let's say I have a German background. We had already hydrogen pipelines before World War II, I guess, right? So where hydrogen was transported to industrial centers in Germany and made somewhere else. I mean, you can distribute it in pipelines and everything. This is old technology, but it costs energy, like everything.
Okay, Brent, I think this might be the end of the line here. It's 12:29 here. Charlie, did you want to come on and give us any last discussion points there? But well, Charlie's. Okay,
Thanks,
there you go.
Joe. Yes, sir.
Yep.
Can everyone see our previous slide showing presentation?
Yes, we see the presenters.
I see myself.
Move on to closing information from AIST. We certainly appreciate your attendance at this 90-minute webinar. We do expect that you'll be able to download the information within a week, as the recording will be there under archived webinars. AIST certainly appreciates your attention from around the world, as we know that people are in different time zones at late in the day and early in the morning. Our hats off to Britt, who's come in Australia at the hours very, very early before breakfast. So thank you, Britt. Our AIST Resource Center is a new resource that we've combined the bookstore and our digital library. For members, please go in and use the search buttons to download more than 10,000 articles, written proceedings, and information that may be germane to your particular technology quest. We'd like to identify upcoming in-person and webinar training conferences. In June, we have a training conference in Pittsburgh, Pennsylvania. We also have the tin plate and decarbonization webinars before AIS Tech. And we all like to say, we'll see you in Detroit in May at the AIS Tech Conference. Thank you for your attendance, and we look forward to seeing you at all future events.